So in this chapter, we turn our attention to the geometric form of the Hahn-Banach theorem. What we've seen is a linear algebraic form, right? It's a statement about the extension of certain linear functional, and it allows us to extend to infinite dimension some fundamental results from finite dimension. Simple things such as the fact that you have a norming functional for every element in your space. Now, this is very useful in linear algebraic type questions in infinite dimension, but we'll find in this course that we're going to use even more a geometric form of the Hahn-Banach theorem, which really can be deduced fairly easily from the extension form that we've proven. And this is theorem 5.2 here that we'll be discussing in this chapter. Now, to explain the statement of the theorem, I need a little bit of vocabulary. So, we'll be always working in the Banach space, and we're going to consider what we call a hyperplane, and that's a subset of my Banach space that is defined based on a element of the dual and a real number. And what you call the hyperplane P alpha x star is the set of all x in X such that this linear equation holds. The duality product between x star and X is exactly equal to alpha. Now, realize that this is really a natural generalization of what you would have in finite dimension. For example, let's do in a two-dimensional space, I could draw that line, right? So line will be a hyperplane in a two-dimensional space, and if this is the point 1 here, then this line is defined by the equation x dot e1, where e1 is this vector here, e1, e2 for my basis of R2 equal to 1, right? So this inner product being equal to a fixed value define this particular line, and then every line actually can be described by such an equation. Now, I'm going to talk about two sets being separated by a hyperplane. So, if I were here, for instance, and I could have some set here and some set there, and I want to say that this set A is separated from this set B, and one way to describe that is by saying that every point in X here, right, if X is in A and Y is in B, then X inner product with E1, the first component of X would have to be smaller than 1, whereas the first component of Y would have to be greater than 1, right? 1 is on the left of that line, that vertical line, and the other one is on the right of that vertical line. So generalizing that idea in a way that makes sense in infinite dimension, we're going to say that two sets are separated if you can find a hyperplane, can find a line like that in two dimension, such that one set is on one side of the line and the other set is on the other side of the line. And that's really expressed by saying that the duality product of x star x is below the threshold that this line defines, whereas the inner product of x star x is above that threshold when x is in B. Right, so that's the notion of separating two subsets of a Banach space by a hyperplane. Now, the separation, here the two sets are even more than separated, they're strictly separated. You could be in a situation, let me draw something else here. You could have, let's say, this square and then this rectangle. Now, they're also separated by a hyperplane. They're separated by this hyperplane here, but really now the inequalities are going to be not strict inequalities, right? Everywhere where this orange line meets the boundary of this square and this rectangle, we're going to have x star x equal to alpha, as opposed to being strictly smaller or strictly bigger. So I want to differentiate from this situation on the left, where I could have some intersection and some elements of both sets lying on the hyperplane, and this situation here where the separation is strict. So we're going to have this notion of being strictly separated, and that's defined now by saying that there is really a gap. So the x star x, when x is in A, are not just smaller or equal to alpha, but is smaller than alpha minus some epsilon. and the x star x are greater than alpha plus some epsilon when x is in B. And the epsilon in that drawing that I had here would be essentially the size of that gap that we have there. Right, that makes sense? So you have a visualization of that separation or strict separation of two sets by a hyperplane. Now, in finite dimension, that would be reasonably easy, although potentially technically painful at times, to find an equation for that line if I give you two sets that you could fit between them. Now, what the Hahn-Banach theorem tells you is that if your sets are convex and one of them is open and they don't intersect, then they can always be separated. Right, so this is in words exactly the statement. Take two non-empty convex sets that do not intersect, assume that one at least is open, then the two sets can be separated. So the keyword here, I've put both keywords in bold. It's extremely important to remember that this is about separation of convex sets, not just general sets, and we're gonna need one to be open in that form of the theorem. Right, so how do we separate convex sets? That's gonna be the part, the key part of this video, proving the theorem. Obviously, this is going to use the extension theorem. This is just a reformulation of the theorem we've seen before. Note, by the way, that you can go from the extension, the linear algebraic version, to the geometric version, or you could prove the geometric version first and then derive the extension version. Both approaches are possible, but we've started with the linear algebraic version. Okay, so the way we're going to prove the theorem 5.2, we're going to have two lemmas along the way. The first one is very important, not just as a lemma, as a step of the proof, but conceptually speaking. It tells you that whenever you have a non-empty convex open set of a Banach space, and let's just assume for simplicity that it contains 0, if not, you could translate this anyway, then any such set, so a convex body that contains the origin, is actually the unit ball for a new norm. And the way you define this new norm is like that. You define rho of x, we call that the Minkovski gauge, to be the infimum of all those alpha such that 1 upon alpha times x is in A. Now you're going to find that this infimum cannot be 0 because, 0 is in A, and A is open. Now, this satisfies all the properties defining a norm, an homogeneity property, a triangle inequality, and this norm will be comparable to the norm that you started with in the Banach space, right? It will be smaller than a constant times the standard norm. And the key thing is here, the set A will be exactly the set of those vectors that have the Minkowski gauge strictly smaller than 1. Right, so we'll be really able to define a norm based on a convex body. And that's one way to think of norms in Banach spaces. They're one way, the set of norms you could put on a Banach space corresponds to all the different convex open sets you might have. Right, so that's the geometric perspective on norming theories of Banach spaces. So once we have this lemma at our disposal and we can construct a topology on X that is adapted to the convex set A, we'll prove a small baby version of the Hahn-Banach separation theorem. And that goes like this. We'll separate not just two convex set, one of them being open, we'll separate a open convex non-empty set from just a single point. All right, so that would be a simpler version of theorem 5.2, and then from that ability to separate one point from a non-empty open convex set, we will prove the general statement. Okay, so let's see how that works. First thing we have to do is prove this lemma 5.3. So show that this definition really gives us a norm that turns A into its open unit ball. Okay, so let's prove the properties of this Minkovski gauge of a convex non-empty open set. So first of all, let's prove property 1. I give myself an alpha, an R, I give myself maybe non-zero, I give myself a beta that is positive, and I give myself a vector. Now notice that asking for x 1 upon alpha times x to be in A, which would be what we need to say that rho of x is smaller than alpha, is literally exactly the same thing as asking for beta upon alpha beta, obviously, of x to be in A. But what is that telling me? It's telling me that if rho of x is smaller or equal than alpha, and that's exactly the same thing as saying that rho of beta x is smaller or equal to alpha times beta. And so because this is true for every alpha, we have that rho of beta x has to be exactly equal to beta rho of x, getting to the infimum. Okay, so that's property 1, that's the homogeneity of rho of x. I'm not going to do property 2, the triangle inequality, quite yet. I'm going to keep that for last. I'm going to do property 3. Property 3, okay, I've got that 0 is in A and A is open. Now, what does that give me? Well, because that gives me a ball, right? That gives me that there is a ball inside A of centered at 0 and with radius delta. And if that ball is inside A, then if I take an x in X and I make X divided by its norm, okay, let's say non-zero, and multiply by, say, delta over 2, then this is going to belong to B0 delta, obviously. And so this is going to be in A. And what does that tells me? That tells me that the rho of x has to be definitely smaller than norm of x divided by delta over 2. Right, and that's going to be my m times x. So m is 2 divided by this delta. All right, so that proves 3 that the Minkovski gauge is always controlled up to a constant by the norm of the vector. All right. Okay. Now, by the way, geometrically speaking, that tells you that you can always include a Euclidean ball inside inside A, which makes sense because that's what open really gives you. Okay, so now when I say that tells you that you can include it inside A, I've already assumed that we've proven 4, which is that A is the unit ball for that Minkovski gauge. So let's prove that. So I want to show that A is exactly the set of those x. It's probably the most important property where rho of x is smaller than 1. So I have 2 inclusions to prove, right? So let's prove the first inclusion, that when x is in A, rho of x has to be smaller than 1. Well, if x is in A, because A is open, we have a small ball around x that has to stay in A. So there has to exist an epsilon such that 1 plus epsilon x is still in A. But if I do that, then this is exactly saying that there exists an epsilon such that rho of x is smaller or equal to 1 upon 1 plus epsilon, and that's certainly strictly smaller than 1. So A has to be included in the set of all x's such that rho of x is smaller than 1. Now what about the other inclusion? Okay, so for the other inclusion, I take x in capital X such that rho of x is smaller than 1. And, well, what does that mean? It means that there exists an alpha positive such that 1 upon alpha times x, oh, and sorry, my alpha has to be smaller than 1, obviously, such that 1 upon alpha times x is in A. But this gives me that if 1 upon alpha x is in A, it tells me that 1 upon alpha x plus what should I say? My alpha is between 0 and 1. That's right. So it tells me that if I take this vector that's in A and I do a convex combination of that, I should say this is only an implication, with another point in A, which is the point 0, then this has to be in A. And that's by convexity of A and the fact that 0 belongs to A, right? So if I do a linear combination, so I take my A here and my alpha here, and I multiply an element of A by alpha, and I add to it 1 minus alpha times another element of A, then I stay in A. But what is that? Well, this is just 0, and this is just x. So I've just proven that x is in A. And that concludes the proof of 4. Now, we have one last thing to prove, and that's the triangle inequality for rho. Let's do that now. So let's give ourselves x and y in A, and let's give ourselves an epsilon to get a bit of room. Now, I have that x divided by rho of x plus epsilon is in A, because maybe x divided by rho of x is not in A, because rho is only an infimum, but if I add epsilon, then I'm definitely below that threshold. And in the same way, y divided by rho of y plus epsilon has to be in A by definition of rho of x and rho of y. Now, by convexity, what do we get? Well, we can take any linear combination of these elements in A and we'll still be in A. So we have that for every t between 0 and 1, t times x divided by rho of x plus epsilon plus 1 minus t times y divided by rho of y plus epsilon as t belong to A. And now I'm going to make a specific choice of t. So I'm going to pick t to be rho of x plus epsilon divided by rho of x plus rho of y plus 2 epsilon. And what does that give me? That gives me that rho of x plus rho of y, sorry, 1 divided by rho of x plus rho of y plus 2 epsilon times x plus 1 minus that. And what is 1 minus that? That's y divided by rho of x plus rho of y plus 2 epsilon as to belong to A. And what does that tell me? That tells me that rho of x plus y can be at most, because with this factor here, you already belong to A, so this is to be smaller than rho of x plus rho of y plus 2 epsilon. But epsilon was arbitrary, so I have the triangle inequality that I wanted. Okay, and that concludes the proof of the lemma about the Minkovski gauge. And really keep the answer in mind. This simple definition, the infimum of alpha such that x divided by alpha belongs to A, gives you a new norm that's comparable to the original norm on your Banach space. And with respect to that new norm, A is the unit open bore. Okay, now that's the trick, looking at properties of that norm that will allow us to move from the linear algebraic formulation of the Hahn-Banach theorem to the geometric formulation of the Hahn-Banach theorem, which is what we're going to do next in a special case where we only separate a convex open set from a point. Okay, so let's see the proof of that. An open, non-empty convex set, a single point not in that set B, can be separated by some hyperplane. So how do we do this? Well, we look at the set B and we define rho as the Minkovski functional associated with B that we have from the previous lemma. So the infimum of those alphas such that alpha minus 1 times x belongs to B. Okay, now I'm going to consider x with rho. So this is still a Banach space because we've shown in the previous lemma that rho is a norm and it's controlled by the norm of x. So Cauchy sequences for rho will be Cauchy sequences for x, and therefore will have to converge. So if it is a Banach space, I can apply the Hahn-Banach theorem in x rho. And I'm going to apply it to extend a linear functional that I'm going to define on just the set A. So on just the single point, well, not just the single point x naught, I should define, because I need to define it on a subspace. So I'm going to define it on the span of that single point x naught, and I'm going to define it as the thing that sends t times x to just t, so t times x naught, sorry, where t is a real number, right? So I'm going to extend that, and we get what? We get an element, let's call it x star, and it's going to be in the dual of x rho, okay, and it's going to be such that x star x, I'm going to avoid using the notation of the duality product because we now have two different Banach spaces, x with its original norm and x with rho. This is going to be smaller or equal to rho of x, that's for every x in x, right? Because when we do the extension in Hahn-Banach, we don't increase the constant in the continuity inequality, and we have that x star of t times x naught. So on this vector space V, which is the span of x naught, this has to match what we had defined on the subspace. So this has to match the linear map G, and that's for all t in R, right? That's the consequence of the Hahn-Banach theorem. Now, this x star is a linear functional from x down to R, and note that x star x is smaller than rho of x, which is smaller than m times x by the lemma that we've proven just before, the lemma on Minkovski functional. That's for all x in x. So x star is also continuous with respect to the topology of the norm on x. So it's an element of the, the original dual of x, the dual defined in terms of the norm topology of x. Right, so we have an element of x star that's going to define our hyperplane, and we just have to show that we have indeed a hyperplane. So I'm going to take alpha equal to what x star does to just x naught. Now, what do I get? So, well, actually, I should say this is going to have to be 1. So I'm going to take alpha equal that, which is equal to 1, since x star of x naught is g of x naught, and the definition of g puts that equal to 1. Okay, and I'm claiming that with this choice of alpha and this choice of x star, I do have my separating hyperplane. Now, why is that? Well, x star of x naught is 1. That's one thing. And what about x star of x when x is in B? So for all x in B, x star of x, well, we know that this is smaller than rho of x, and rho of x is smaller than 1 for all x in B. That's again by the lemma. Alright, we've proven that B is exactly the set of all x's in capital X such that rho of x is smaller than 1. So we are smaller than 1, so in particular smaller or equal to 1 on B, and for x equal to x naught, so for all x in A, where there's only 1 point, we have x star of x equal to x star of x naught, which is equal to 1, which is certainly smaller, greater or equal to 1. So we've proven that this hyperplane defined by x star and alpha does separate A from B. And that concludes the proof of that lemma. So we've proven the geometric form of the Hahn-Banach theorem in the special case where the potentially non-open set, well, non-open in that case, is a single point. Okay, so at this stage, the proof of the general theorem is fairly easy. It's essentially a corollary of the lemma, which itself was a corollary with the appropriate ID coming from Minkovski gauge of the extension version of the Hahn-Banach theorem. Now let's see the trick here. So the trick is to separate a appropriately constructed set from the point, the single point 0. So I'm going to define the set Y, sorry, which is the difference of the set A and the set B. So the set of all vectors in X that are of the form U minus V for some U in A and some V in B. Now that is convex. You can do that as an exercise, right? Because it's differences of elements of convex sets. And this is non-empty, I mean, it contains A for that matter. Okay, so I have a non-empty convex set. I want to separate it from the point. I need to know it's open. And the fact that just B is open is going to be enough to make Y open. Because what is Y? I mean, Y is really the union over all U in A of the set of all vectors of the form U minus V, where V is in B, right? But, okay, but now B is open, so the set of all points of the form U minus V with V in B is also open, and now I'm taking a union of open set. So is open as a union of open sets, right? And this is really why we don't have the symmetry of assumption. We only need openness on one of the sets, B, because the set that really matters in the separation theorem is the set of differences. And the set of differences is going to be open as long as one of the two sets is open. And now all we have to do is separate the differences from 0, right? We really want to separate the value of the duality product on two things, and that's really the same thing as separating the difference of the two from just the number, from just 0. So now 0 is not in Y because A does not intersect B. If 0 were to be in Y, then there would be a U in A and a V in B, such that U is V. Okay, so the fact that the two sets don't intersect is very important to be able to run that argument. And now by the lemma, what do we have? We have that we can separate Y from 0. So there exists an X star and capital X star such that, okay, with which alpha, by the way? Well, with alpha equal X star of X naught in the vocabulary of the lemma, and X naught here is 0. So with the parameter alpha equal X star of 0, and which by the way is 0, and functional X star, this hyperplane will separate Y from the single point 0. But what does that mean? Okay, well, it means that you take any U in A and any V in B to have a generic element of Y, and I have that X star of U minus V has to be smaller than X star or equal than X star of 0, which is 0. And what is that telling me? Well, it's telling me that for all U in A and for all V in B, X star U has to be smaller or equal to x star v. But now that also tells me I can take a supremum and an infimum on each side. So that tells me that the supremum over all u in A of x star u is smaller or equal to the infimum over all v in B of x star v. Now these two things may or may not be equal, but whatever. I can pick an alpha between this supremum of x star u for u in A and the infimum of x star v for v in B. Maybe there's a single possible choice, maybe there's plenty of choices, in which case I just pick one, and then we have that for every u in A and for every v in B. X star u, well, it's smaller than the supremum, so it's smaller than alpha, and x star v is greater than the infimum, so it's greater than alpha. And that concludes the proof of the geometric form of the Hahn-Banach theorem.